this earthquake brought to you by the hands of me. All right, so let's take a look at a couple miscellaneous things that I sort of flew over last time. I believe we did talk about that if you have two parallel plates of opposite charge, you have a constant electric field between them, or at least it's a decent approximation. So I have these two parallel plates. I'll make this some charge Q and this charge negative Q. And so I am going to assume that we have a constant electric field. Now, in reality, the closer you are to the edges, the less uniform it is. And the farther apart I spread them, the less uniform it is. Although I'm still surprised that there's a lab that you'll do probably next week where the distance between them is rather large compared to the size of the plates. And let's look at a nicely uniform field there. Or more so than I would expect. So the arrows represent the electric field. And into this, I'm going to shoot a charged particle. So I have some charge Q, which I'm going to shoot into it. First off, I drew the electric fields going down. Why are they going down?
Because they go away from positive and towards negative.
There you go. If Q is a positively charged particle, what's going to happen to Q when I shoot it into this uniform electric field?
It'll want to move down.
Say it again?
It'll want to move down.
All right. And so as it comes in, let's say that that's the original line of path. It will end up something like that. It will start to deflect almost instantly. But it's going fast enough. Generally, this is the type of thing that you would see in high energy experiments. And something like this allows you, if I can adjust the charges here, if I can adjust the charges that are on those plates, I can change how much a particular particle is deflected. And so one of the things that you can deflect it with magnetic fields or electric fields. And so one of the things that the people in the control room do is if the beam starts to seem like it's getting a little bit off center, then you just adjust that and bring it back to where you need it. So if I think about this sort of, the line, after it leaves, it should be traveling in a straight line again, and I want us to sort of figure out what theta is. I am going to assume non-relativistic. That is something that we will hit later on in April. So the initial velocity of Q is equal to V naught I hat, and so let's just go ahead and establish I hat that way. And just to keep things positive, we'll make J hat down. If the electric field is constant, the force on the particle is constant. If the force on the particle is constant, then the acceleration is constant. And I can use the constant acceleration equations, or for those who have had me before, what I refer to as the cake formulas, constant acceleration kinematic equations. Constant acceleration kinematic equations. Lay it on me. Come on, what are they? Off memory. This was the moment that you were going to impress me. I was going to be wild. I have tears of joy streaming down my face. What was it, Faith?
Give me a small clue. They're like right there.
You got VF equals, you got VF squared equals, you got delta SRX, whatever letter you're using for position, equals, and some textbooks will have 5, in which case there'd be another delta S.
I can see a lot of letters. It's like velocity formulas.
And again, one of the reasons I'm doing this is to sort of brush off some cobwebs.
I think one of the bottom ones is, times the initial, or is the initial times t plus, acceleration times time squared.
1/2. Yep, that's one of them. And that's the one that we actually, well, no, actually we'll be using the first one. Okay. VF equals VI plus AT. In essence, it's the first derivative of this with respect to time. VF squared equals VI squared plus 2A dot delta S, which can also be derived from conservation of energy. And the last one is displacement just being average velocity divided, or times time. And average velocity if acceleration is constant is VI plus VF over 2 times time. There are other variations of this depending on which textbook you were using. I put VF here, but some textbooks will just drop the subscript F, figuring the final velocity or speed or whatever. Final is always that moment of the problem when you're looking at it. And some textbooks will use delta T instead of just plain old T. And then the symbol for position, I'm using S here generically. R is often used. Some textbooks will stick with X and Y and Z. I tend to use X usually, but not this time. All right, so take a look at the first one. My final velocity, in other words, my velocity as after it's been shot out here, is equal to my initial velocity, which I gave you. It's traveling at some speed to the right. And then the acceleration times time. How do you find acceleration?
Do the derivative.
Except in order to do the derivative, we would need to know the formula for velocity, which we can't find until we have acceleration. Or we need the formula for position or displacement, which we can't do until we have acceleration. But that is one method that traditionally is used. What's the other way you find acceleration in physics? That was the math answer. All of you know it. Whether you know what I'm talking about right now or not, you will when it's mentioned, or you'll go, oh, of course.
Is it setting two force equations equal to each other? Because I was thinking it's using the one we went over last time, Q times the electric field, and what was the other one? Acceleration, times force equals mass times acceleration.
Yes, there you go. That's what you're using.
Okay.
Newton's second law, F equals ma, or acceleration is force divided by mass. That's what I was talking about. The other way, so you can find acceleration using the map definition, which was Devon's approach, or in this particular case, since we don't have enough information to do it by pure math, we have to use one of the few physics equations from the first semester course. And as we've established, the force is going to be Q times the electric field, or I guess in this case, capital Q, divided by the mass. The electric field is in the J direction, so I can write this E vector symbol here with Q, E, J hat over M. And my Q's and thetas look too much alike, so let's see, distinguish them slightly. So I plug in here, Q, E over M. And I do want to distinguish that E right here in this problem, E is equal to the magnitude of the electric field. It is not energy. All right, so now time. The time we're talking about is the time it's exposed to the electric field. In other words, the time it takes for the particle to get from here to here. If we establish that the electric field takes place over some length L, my horizontal velocity does not change at all. All the force is vertical, and so the horizontal stays constant, just like a projectile motion problem. Matter of fact, this parabolic path while it's within the electric field. So using, let's use the fourth equation there. Horizontally, there's no acceleration at all, and so the fourth equation just becomes L is equal to V naught T. So T is equal to L over whatever that initial speed was. And so we can now make that substitution. L over V naught. Lost my J hat. There we go, J hat. Questions to hear? All right, so I know what the final velocity is, and I'm trying to find that angle. Well, my final velocity is in that direction. That's a right angle there. This is theta. If I had some way of figuring out what the ratio of the sides are of this right triangle, I can figure out theta, and lo and behold, we have it right there. The horizontal component is proportional to V sub naught. My vertical component is proportional to Q E L over M V sub naught. And so theta is the arctan of Q E L over M V sub naught squared. That opposite over the adjacent. Now, in terms of some of the math that I do in here, all of you have had Calc 1 and are, no, you've had to have had Calc 2 by now. Also, we're hitting upon the people who learn calculus at home because of the pandemic. So I am making certain assumptions about the math that you do know, obviously not using calculus here, but the math that you do know. Just please raise your hand if I do anything. This is sort of a generic comment, not necessarily about right now, but if I'm doing any math that it's been too long, or you had to learn it on your own, just stop me. I'd be glad to go over it. But I am making some assumptions about how much math you do know. Correctly or incorrectly, I'm making the assumptions. All right, any questions up to here? All right, so recognize the other power of this is not just high energy experiment. I can tweak the dials a little bit and I can get the beam to start shooting off in a different direction, but it also allows us for particle selection. Suppose I want a bunch of protons. I make an electric field high enough, I send a bunch of hydrogen through there, it rips the hydrogen out because the electrons are going to get pulled this way, going to be pulled up, and the protons are going to be pulled down. So just sending hydrogen through here, I can now have separation of two particles, and if I can somehow collect them, which is possible, I can now have some really nice elementary particles. Technically, a proton's not an elementary particle, but we're going to go with it. We have some basic particles, that's probably better wording, basic particles that I can now slam into targets for high energy experiments. if I'm sitting through a whole stream of particles, this is another benefit of this. If let's say that I have a bunch of protons and I have some target right here, and I shoot the protons, several million protons at this target, what's gonna happen is it hits the target and now I'm gonna get a spray of particles out. There's gonna be lots of collisions. These collisions, we get this huge spray of particles. If I send the spray of particles through here, positive charges go one way, negative charges bend the other way. But also, if I got a detector here, and a detector here, and a detector here, I can start to identify what's coming out of this, because Q I have control over, which controls the electric field. The length is something I control also. Oops, try that one again. I don't control Q. I control, yes, because Q is the particle that's being shot. I control the electric field. I control how long that my capacitors are. My initial velocity I have some control over. What I don't control here is Q over M. And that is a nice identifier for particles. If I have charge divided by the mass, it quickly narrows down what is coming out. Ah, I see my problem here. I use capital Q 2 different ways. The charge on the plates, Q and negative Q, and then I had a separate charge over here. That was bad form. Why don't we call this Q1 and Q1? Because that Q is that one. Let's just do some quick number crunching here. I want to keep it non-relativistic. The faster these particles are to the speed of light, the more you really have to, things change. So, yeah, the faster an object goes, the slower its time runs. And I wanted to ignore that. So, speed of light is about approximately 3 times 10 to the 8th meters per second. Generally, you start bringing relativistic effects into it at about 10% of that. So why don't we just shoot for V naught being 2 times 10 to the 7th meters per second. Let's make it a proton. And the mass of a proton is, you could think, or I could actually just look it up, 1.67 times 10 to the negative 27th kilograms. The charge of a proton is
10, no.
Just coulombs.
just coulombs. Let's make the length of this 0.5 meter. And, I need to know what the electric field is here. I'm trying to think of a realistic number. I'm not coming up with one off the top of my head, and so I'll just make something up. Let's make it, the electric field strength is 100 newtons per coulomb. I'm assuming that's sort of what you were thinking of when you said Newton coulombs. Let's see how much we're deflecting those protons. So the angle will be the arctangent of 1.6 times 10 to the negative 19th times my electric field of 100 times
0.5.
over my mass, which is 1.67 times 10 to the negative 27th, times my speed of 2 times 10 to the 7th squared, and this is looking like it's gonna be it's gonna be a tiny number. Yeah, my electric field strength is too low. But we can still do it anyway.
So,
6, 4. Sorry, I'm not necessarily asking for it in radians, I just, I can do for tiny angles, I can do it in radians more easily in my head. Although it's still way off. Actually, it should be a little less than that, so let's adjust to, what's the real answer?
I got 0.000686.
Is that radians or degrees?
I got degrees.
Which is exactly that in radians. You have 3 zeros in the 686?
Yep.
Then I'm off, oh, I'm off by a 0, at least 1 0. What is it, radians? How do you,
I gotta plug the whole thing in again.
oh,
You good?